Here I have a large wheel that's released from rest on a 30-degree incline and allowed to roll down. It's attached to the top of an incline by a spring with a spring constant of 3 pounds per inch. My question is, if the wheel is released from rest while the spring is initially unstretched, how far does it roll before it has a velocity of 1.5 feet per second? And this big wheel has a mass of 40 pounds, a radius of 0.8 feet, and a radius of gyration of 0.6 feet. That should be everything you need to solve it. If you want to try and get started on your own, do that, and come back when you're ready to see the solution. When I first see this problem, I'm seeing velocities and some distances, how far, masses. I'm immediately thinking work energy principle or conservation of energy. And I'm going to solve this using conservation of energy. So my conservation of energy equation, the kinetic energy at state 1 plus all of the potential energies at state 1 plus the non-conserved work between states 1 and 2 is the final kinetic energy plus the final potential energies. So here we start from rest, so I have no initial kinetic energy, favorite situation. And initial potential energy, if my spring is initially unstretched, I don't have any initial potential energy, or spring potential energy. But if it's going to fall down this hill, then I do have initial gravitational potential energy. So I will have mgh1. All of the forces here are conserved: springs, gravity. The friction doesn't do any work, so I don't have to worry about that because it's not kinetic friction, it's only static friction. So there's no non-conserved work here. All right, so this should go to my final kinetic energy. So I do want to know when it has some kinetic energy. So I will have a 1/2 mv squared. That's the mass moving, but it's also rolling. There's also some kinetic energy, rotational kinetic energy. So I have also a 1/2 I omega squared term in my kinetic energy here. Include both those terms. And then final potential energy. As it rolls down this hill, this spring will stretch. So I will get some spring potential energy. So I'm going to include that here, 1/2 ks squared. But I think at the final position will be the lowest I will consider, so I don't need to worry about final gravitational potential energy. I think that's all of my terms. Conceptually, that makes all sense to me. Now I just need to go through mathematically and see if I can make it work out. So my mass I know is 40 pounds, g, and then h1. This is tricky because I'm trying to figure out kind of how far it rolls, really this like S2 distance. And so my S1, or my H1 here is this height. This angle is 30 degrees. So I think my H1 will equal my final stretched length S2 times the sine of 30 degrees. A little bit of conceptual trig there, but that should work out. So if I use that, then I'll still have my final distance as my unknown. All right, then 1/2 my mass I know, my final velocity I know. 1/2 I omega squared. So my mass moment of inertia I'm going to need to solve for. My mass moment of inertia here, I'm given the radius of gyration, so I'll just use my mk squared to figure out my mass moment of inertia. This is k2. It's not. So I can solve for my mass moment of inertia. And then my angular velocity here, like most coupled motion problems like this, it's just going to be my velocity divided by my radius. So I can use that for my angular velocity, my kinetic energy term. 1/2 my spring constant I'm given, and the S2 is what I'm trying to solve. So with that little bit of trig and some rotational components, I'm ready to solve this problem. So mass 40 pounds, when in doubt, convert to slugs. So I'm going to go ahead and convert to slugs here. And then I'm immediately going to multiply by 32.2 feet per second squared. So you could have just done the mg is equal to 40 pounds is fine. And my h1 I said again was S2 times the sine of 30 degrees That is my left-hand side. And now equals, I'm going to have to move to the next line, my right-hand side. So I have 1/2 my mass, when in doubt, convert to slugs, times my final velocity, 1.5 feet per second squared. All right, plus 1/2, now my I'm going to use mk squared. So 40 divided by 32.2 slugs times my k is 0.6 feet times my omega squared, that's going to be my V2 over R. So this will be my 1.5 feet per second divided by 0.8 feet squared. Plus, one more term, 1/2 my k. This k is my spring constant, so 3 pounds per inch. Everywhere else I'm in feet, so I need to convert to feet here too. So don't forget there's 12 inches in a foot times S2 squared. My only unknown now in this equation is that final displacement S, and this is a quadratic. So using the quadratic formula, we solve for S. We'll get two possible solutions here, and my S2 is either 0.1223 feet, or my S2 is 0.9883 feet, or 884 maybe feet. Either of these answers, it makes sense and totally work. And in fact, what's happening here is that it starts from rest, it accelerates, it reaches some maximum acceleration and then begins to decelerate. It stops and rebounds. And so it actually reaches this velocity of 1.5 feet per second twice. Once after it's gone about 1 inch and one after it's gone maybe 11, almost 12 inches. So it kind of very quickly reaches this velocity, and then it's going faster than that, and then it starts to slow down again. It stops and rebounds up. So we have two potential distances at which it's going 1.5 feet. If I want to know the first, or 1.5 feet per second, if I want to know the first time that it reaches 1.5 feet per second, it'll be this initial lower S value, 0.122 feet. But I would accept either answer in this problem.